these are the basics of what you're going to need to know to prepare your kinetics design lab. So starting out here, just a little intro into what is the rate of the reaction. It's measured based on the change of concentration of the products divided by the change in time. Now this is a very difficult thing to measure directly, so we end up measuring things that are related proportionally to the concentration in order to determine that rate of reaction. We're going to talk about some of those ways here. We also want to remember that eventually we're going to be collecting data, and that data is going to give us information for a graph. And if we have that information on the graph, we are able to determine the slope of the line at a specific time, and that slope is equal to the rate at that time. So one way to measure, instead of directly concentration, we can measure the volume of a gas. And this works especially well if we are dealing with a light gas like hydrogen. So we've got an Erlenmeyer flask with a stopper and a tube. The tube goes into a water bath, and that water bath has a test tube in it. And the test tube or graduated cylinder is going to be even better, is going to measure the amount of gas that is produced over time. And so with each 30 seconds or so, we can measure down the new time, and that time will allow us to determine the data for the graph, which will then allow us to determine the rate at a specific time. The mass of reactants is another item that we can get data for if we've got a heavy gas like carbon dioxide. So as we put a beaker with the reactants on the scale, we can measure that initial time, and then as the gas is produced, the gas is going to escape the beaker, and so your mass is going to decrease. This decrease in mass would be that change in concentration over a set time. So every, again, 30 seconds or so, you would be measuring the new mass that would be decreasing. One way to do it, if you see a problem that says that you've got an acid or you're creating a base or something like that, you could do titration. But the problem with titration is that you have to have a really slow reaction, or you need to stop the reaction midway through to see what it is at each of the different times that you've selected. So with anything that you would do in our lab, this is just not a feasible situation. Again, however, you would need to be able to look at a problem and say what type of measuring you would do, and if you saw something about acids and bases, this would be a good option for you to select. Another option would be the rate of light absorption. So this works well for things that are producing a precipitate from two aqueous solutions. The time for that precipitate to obscure a mark made on a piece of paper would be a good indication of how we are producing at a different concentration over time. Or we could compare a change in color over time, or we could use a spectrometer to measure a color absorbed by a colored precipitate. Again, this would be one that we're not going to do in the lab because of the materials that we have. However, it would be one that you would need to identify on an examination as a way to measure if a precipitate is produced. Another item would be measuring electrical conductivity. And so this relates a little bit to what you were learning in redox reactions. We can measure a current's resistance over the creation of ions. So if you saw a problem that said you're creating ions, you would say, oh yeah, we can use electrical conductivity. Again, this is not something you will be doing in this lab. One thing that we need to understand in the background information on the lab experiment you're going to do is collision theory. So collisions have to occur for a reaction to take place. If you have two atoms and they're separated and they're not hitting one another, they're not going to create a new compound. So the electron clouds want to repel each other. We've got negative and negative. They're going to want to repel each other unless there's enough kinetic energy to make them collide. So kinetic energy is the energy of motion, or speed is sometimes used. But there's a minimum amount of energy to break and make bonds. and that's called the activation energy. So the activation energy is that minimum amount of energy required for a reaction to take place. We have a capital E for energy, and the subscripted lowercase a is what makes us know that this is the activation energy. It has a unit of kilojoules per mole, and it's going to change based on the reactions that we have. Some require much less energy than others. And here's that energy level diagram that we saw before in chapter 5, I believe. We see that the activation energy is that bump in the reaction diagram. Another thing that we have to worry about is called steric factors, and that's that all molecules have to be oriented correctly to bond. So if we've got two big organic molecules coming in and hitting one another, but they're hitting in a bad location like we have here, those things don't want to bond. It'd be, if we look down here, we want to take one of those hydrogens from it, or whatever this is, and so this way would be effective. But when those two hydrogens hit each other, they're not going to form something else. The bonds that they have with their oxygens are stronger than they are with than they would be with each other, and so that's just not going to work. So the direction or the way that they hit is important as well. This is called a Maxwell-Boltzmann distribution, and this curve is different than we normally see in science. It's what's under the curve that matters. So all of these are saying I've got a bunch of particles, because the graph goes up high, got a bunch of particles in this area that are going to have a high kinetic energy or a low kinetic energy, but not higher than the activation energy. And even if these hit in the right orientation, they're not going to have a reaction because their activation energy is not high enough. Notice over time, as we're increasing that activation energy, less and less particles have the right energy to create a new compound, even if they are having the correct steric factors. And we're going to get back to this Maxwell-Boltzmann distribution in just a little bit. Again, this would be for background information in your experiment. Okay, things that we can change that are going to affect the rate of the reaction. One of them is temperature, and this is one that you could do in the experiment. You could change the temperature, which is a measure of the average kinetic energy of a substance, to make the particles move at different speeds. Higher temperatures mean more particles are moving faster. And this should result in more collisions, and since the particles have more kinetic energy, more of the collisions should result in a successful reaction than they did at a lower temperature. So, in summary, increased temperature is an increased rate of reaction. And this is what it does to that Maxwell-Boltzmann diagram. So, my original one is here. It has a higher peak here, and it's kind of like I've smushed down the chart. In smushing it down, I have less particles in the original part and more particles that are going to have enough kinetic energy to make the reaction occur. Another thing that you could change in your experiment is concentration, and this works specifically with aqueous solutions. An increase in the concentration of the reactants means that there's more reactants present. If there are more reactants present, there's going to be more collisions more often, and so increasing the reactant concentration should increase the rate of reaction. And this is why the rate of reaction decreases as reactants are used up, because over time there's less reactants, so less collisions, and therefore less products being formed. Another thing that we can change is particle size. In the experiment, you can do this either with choosing the 5 different options for calcium carbonate, or by chopping up the 2 centimeter pieces of magnesium to different lengths. The shorter the length, the more surface area. So as particles get smaller, the surface area, or the spots where reactions can occur, increases. So think if you take a sugar cube and you use that same mass of sugar just from a spoon, those things are going to react, or let's say dissolve in water faster or slower because of the amount of surface area. So the spoonful of sugar, as you dump those little sugar particles in there, even though it has the same mass as the sugar cube takes a longer time to dissolve. So more surface area means more contact between reactants. So smaller particles, which have more surface area, means a higher rate of reaction. If we had gases, pressure would be something that we could alter as well. In this experiment, you are not given anything that has gases as reactants, and so we won't be using this one in this experiment, but you do need to know it potentially for examinations. So a reaction involving gas reactants, the pressure has the same effect as concentration does. So a higher pressure means more particles are confined to a smaller space, and this results in a higher rate of reaction because the particles collide more often. Another thing that we could do is add a catalyst. Now, again, this isn't going to be one that you can do in your experiment that you are designing here, but it is something that you need to know about. So a catalyst is a substance that increases the rate of reaction, but it's not actually used up by the reaction. So it's not a reactant, it's just used in the experiment. And catalysts do this by lowering the activation energy for the reaction. And that is all. You should have enough information from this now to successfully complete your experimentation.